Chapter 6 Synchronization Tool Online Background The Critical Section Problem Peterson Solution Hardware Support for Synchronization Mutex Lock Semaphore Monitor Live Need Evaluation Background Processor can execute concurrently. Concurrent access to shared data may result in data inconsistency. Maintaining data consistency requires mechanics to ensure the orderly execution of cooperating processes. We illustrated in chapter 4 the problem when we considered the bounded buffer problem with user of a counter that is updated concurrently by the producer and customer, which lead to race condition. This race condition critical section problem. Consider system of n process P0, P1 to Pn minus 1. Each process has critical section segment of code. Process may be changing common variable, updating table, writing file, etc. When one process in critical section, no other may be in its critical section. Critical section problem is to design protocol to solve this. Each process must ask permission to enter critical section in entry section. May follow critical section with exit section, then reminded section. Critical section. General structure of process PI. Critical section problem. 1. Mutual execution. 2. Progress. 3. Bounded waiting. Interrupt based solution. Entry intersection disable interrupt. Exit selection enable interrupt. Will this solve problem? Software solution 1. Two-process solution. Assume that the load and store machine language instruction and atomic add that is cannot be interrupted. The two progress share one variable in turn. The variable turn indicates whose turn it is to enter the critical section. Initially, the value of turn is set to I. Algorithm for process PI. Correctness of the software solution. Mutual execution is preserved PI. Enter critical section only if turn equal I, and turn cannot be both 0 and 1 at the same time. What about the progress requirement? What about the bounded waiting requirement? Peterson solution. Two-process solution assume that the load and store machine language instruction atomic atomic that it cannot be interrupted. The two processes share two variables. In turn, Boolean flag 2. The variable turn indicates whose turn it is to enter the critical section. The flag array is used to indicate if a process is ready to enter the critical section. Flag I equal to imply that process Pi is ready. Is algorithm for process Pi. Correctness of person solution probable that the three ch6 requirements are met. 1. Virtual execution is preserved. 2. Process its requirement is satisfied. Bounded waiting requirement is met. Peter solution and modern architecture are thought useful for demonstrating an algorithm is Peterson solution is not guaranteed to work on modern architecture. To improve performance, processor and or compiler may record operations that have no dependencies. Understand why it will not work is useful for better understanding race conditions. For single thread, this is okay as the result will always be the same. For multi-thread, the recording may produce inconsistent or unaccepted results. Model architecture example: to treat to thread share the data. Here, thread 1 perform, thread 2 perform. What is expected output? The output is 100. Modern architecture example: count. Peterson solution revisited. The effect of instruction reordering in Peterson solution. This allows both process to be in the critical section at the same time. To ensure that Peterson solution will work correctly on modern computer architecture, we must use memory barrier. Memory barrier is memory mode. The memory guarantees a computer architecture make to application program. Memory mode may be either strongly ordered, weakly ordered. Is strongly immediately, is weakly not be immediately. A memory barrier is an instruction that forces any chain in memory to be propagated to or other processor. Its memory barrier in such instruction. Therefore, even if instructions were recorded, the memory barrier ensures that the store operations are completely in memory. Memory barrier example. Synchronization hardware. Many systems provide hardware support for implementing the critical section report. Uniprocessor. We will look at 3 forms of hardware support. Hardware instruction, atomic variable. Hardware instruction, special hardware instruction that allow us to either test and modify the content of a word or to swap the content to word atomically. Test and set, compare and swap. The test and set instruction property executed atomically. Return the original value of passage parameter. Set the new value of passage parameter to true. Solution using test and sets. Set Boolean variable log initialize to false. This solution. The compare and swap instruction property executed automatically. Return the original value as parameter value. Set the variable value, the value of the passage parameter new value, but only if value to equal expect. It is true that if the swap takes place only under this condition. Atomic variables. Typically, instructions such as compare and swap are used as building blocks for other synchronization tools. One tool is an atomic variable that provides atomic. For example, sequence, increment, variable sequence. The command multi-locks. Previous solutions are complicated and generally inaccessible to application programs. OS design building software tools to solve critical section problems. Simple multi-lock. Simple is multi-lock. Boolean variable indicating if lock is variable or not. Protect critical section by first acquire, then release. Call acquire and release must be atomic. Usually implement via hardware atomic instruction such compare and swap. But its solution requires precise binding. This lock, therefore, called a spin lock. Solution to CS problem using multi-locks. Semaphore. Semaphore is synchronization tool that provided more sophisticated rather than multi-locks. Semaphore S. Integer variables. Semaphore count is counting semaphore, binary semaphore. very simple, same as the mutex blocks. Semaphore usage example. Solution to this problem. Semaphore implementation must guarantee to no two process can execute the wait and signal. Semaphore implementation with no pussy waiting. With each semaphore, there is a associated waiting queue. Each entry in a waiting queue has two data items, two operation block and wake up. Wake up is remove one of processes in the waiting queue and place in the ready queue. Implementation with the Busy waiting count. Waiting queue. Problem with semaphore. Incorrect use of semaphore operation. This and order are. This and order are. Example of what can occur when semaphore and other synchronization tools are used incorrectly. Monitor a high-level abstraction that provided a convenient and effective mechanism for process synchronization. Abstract data type internal variable only accessible by code with with in the produce procedure. Only one process may be active within the monitor at a time. We pseudocode syntax of a monitor. Schematic view of a monitor. Monitor implement using semaphore. Condition variable. Monitor with condition variables. Liveness. Process may have two with I identify will. Process may have two with identify while trying to acquire an synchronization tool such as a mutex lock or semaphore. Waiting indefinitely while violate the progress, and bounded waiting criteria discusses, discusses, and the beginning of this chapter. Liveness refers to a set of properties that a system must satis- satisfy to ensure processes make progress. Identify waiting is an example of a liveness value. Liveness deadlock. 2. The more processes are waiting identifiably for an event that can be caused by only one of the waiting pockets. Thank you.